Okay, the math professor is on the air once more. And good afternoon and welcome to Computer Aided Manufacturing class. Today we will be going through Chapter 7 of Groover's book, Automation, Production Systems, and Computer Integrated Manufacturing. I am your genial host, Harry Whiting. All right. Chapter 12 is about automatic identification and data capture. So we will be discussing these four sections of Chapter 12. But first, we'll discuss what is automatic identification and data capture. Well, it's any of a family of technologies that give direct entry of data into a computer or other microprocessor control system without using a keyboard. We have three reasons we might want to use automatic identification and data capture. One is data accuracy. Two is timeliness, and three is labor reduction. Okay, so, of course, with manual collection and data entry, we end up having three overarching problems. First is human error. When data is collected and entered manually, it's very easy to be entered ambiguously. Numbers are get switched, or something, an entry is unreadable. The time factor, we may have too much of a delay between when things are actually happening and entering the data associated with those events. That is not to mention that there is a time-consuming aspect to entering things manually. Even if it's being entered in, quote, real time, unquote, there is a delay. And then we have the problem of the labor cost. There is a cost anytime human beings have to attend to something instead of it having to being done manually. So anytime we can reduce cost, of course, we want to do that. So what are some applications that we might have for automatic identification and data capture? Well, in retail sales and inventory control, we are definitely seeing, or have seen, a huge revolution. Instead of having to count things by hand and input that by hand into a data sheet or into a computer, now this can be done much more quickly using machinery. Material handling for shipping and receiving, sorting, order picking, mail and parcel handling, there's been a huge revolution. And this is not a new thing. The mail service started sorting mail a long time ago using a barcode that only they use at this point. For factory operations, we can have order processing, tracking of our work in process, tracking of machine utilization, and worker attendance. In fact, when I worked for the Center for Automatic Identification at Ohio University, Dr. Barisso would issue each student a little RFID strip that they would keep in their wallets, and so it would automatically record their attendance when they came to class. Some other applications that are being used: patient identification in hospitals, check processing, security systems, right? And really the sky's the limit. Anytime we need to figure out a way of quickly and accurately capturing data, we can usually do it using these automatic identification and data capture methods. All right, so what are the components of an automatic identification and data capture system? Well, nearly all of these technologies use three components which mirror the sequential steps of automatic identification and data capture. First is data encoding. Our alphanumeric characters are translated into a form that can be read by a machine. Then we have the machine reading and or scanning, where a scanner reads that encoded data and encodes it onto a memory of some kind, usually as an electrical signal. Then we have the data decoding, where that electrical signal is transformed back into digital data and then back into the alphanumeric characters. The day may come when the alphanumeric characters aren't needed because there are no humans in the system, but luckily that day is not yet. All right, so what kind of technologies do we have? Well, the first is optical, where we have barcodes. Those can be linear barcodes, such as a UPC code, or 2D, where we have stacked barcodes. We have optical character recognition, where machines can actually read alphanumeric characters and translate those, and machine vision. The second type is electromagnetic, where radio frequency identification, or RFID technology, is in use. And the third is magnetic, where data is encoded magnetically, such as on your credit cards where you have a data strip that's magnetic tape, or bank checks sometimes have these kind of magnetic strips on them. Another technology is the smart card, where we have plastic cards that are embedded with microchips, and those are essentially just integrated circuits. So, for example, you may have in your wallet right now a credit card that has a chip in it. We do have some touch techniques, such as touch screens, and those are becoming more and more available and popular. And we can have biometric technology, where we have instant voice recognition, fingerprint analysis, or retinal eye scans. All right, so of course we have to be able to say how accurate is our reading of these technologies. One way we measure that is the first read rate, or FRR. So the probability of a successful reading by the scanner in its initial attempt. Then our second measure is the substitution error rate, or SER. Of course, for those of us who are professional engineers, SER means serial experience record. But I digress. So this is the probability of the scanner incorrectly reading the encoded character as a different character. So in a given set of encoded data within characters, the expected number of errors is the SER multiplied by N. Simple statistics, really. All right, so our barcodes are of two basic types. The first is linear, where encoded data can be read by a sweep of the scanner. And then there's two-dimensional, where encoded data has to be read not only in the X but in the Y dimension. All right, essentially we only have two kinds of linear barcodes. Width modulated, where our symbol is bars and spaces that have varying widths, right? This is very widely used, and one of the first technologies to use barcodes was the Universal Product Code. Then there's height modulated. This symbol is bars and spaces of varying heights. At this point, this is used only by the U.S. Postal Service for zip code identification. So if you if you receive a letter from the post office, you will see it's got a barcode with different heights. And we're going to take a look at that right here. So here we have an example of the Universal Product Code, or UPC, right? Where we have lines and spaces, and again, the lines and spaces have varying widths. so that that can be read into a machine and be eventually put out as an alphanumeric code. Right? We also have the numbers here to back that up. The height modulated barcode is used by the U.S. Postal Service, and it's every 5 bars is a number. But you read it by if a bar is tall, it is read. If it's short, it is left out as not being part of the number. So the first number here would be 6, I believe, on that barcode. All right, so there has been an attempt to use Morse barcodes, but only the dark bars are used, the spaces are not used. So it's a longer coded symbol. And for different letters, you have different numbers of characters. So it makes it uncertain as to how long it will be. All right, so when we're reading the barcode is turned into an electric signal pulse string. So this light beam sweeps across and it reads either as a 1 for the bars and a 0 for the spaces. That is then translated into an electrical signal, and this would be the electrical signal that we would read from that. All right, so there are various barcodes and ways to read them, and here is the USD2 character set, right? And it goes from 1 through 9 and 0, A through Z. Then we have these characters are so tiny I can't read them. All right, but again, this is just for illustrative purposes. So we can have linear barcode readers, which are either contact readers. In that case, it's a handheld wand or a light pen that we move the tip through the barcode to read it. We can also have non-contact, where the reader just focuses a beam on the barcode and the photo detector reads the reflected signal. So that can be a fixed beam or a moving beam. In a moving beam, our light beam traverses through an angular sweep searching for the barcode. All right, so here we see a system that has been set up where we have a stationary moving beam barcodes scanner. It's scanning up and down, and as each barcode comes in, it's reading it so that it is able to account for these products or possibly send them to the correct place for shipping, etc. All right, so we saw the first 2D barcodes in 1987. The basic types of 2D barcode symbols. First of all, there's stacked barcodes, where it's just the ordinary line and space barcode, but shortened, and then a bunch of them are put on top of each other. Then we have matrix symbologies. So those are 2D patterns of data cells. Usually they're square and they're colored dark or white. Their advantage is they can contain more data. So here we see a 2D stacked barcode, and each of these individual lines is able to be read as a separate piece of information that goes into the system. The 2D matrix barcode I have to confess, I do not know the deep ins and outs on how those are read. All right, so radio frequency identification. Our RFID has an identification tag that has the coded data, and it's attached to our item. So the tag has a memory microchip and an antenna. Often that's encased in a plastic container, but not necessarily. Great strides have been made in the RFID area to the point where now you'll even have RFID tags that are thin enough that, for example, they're put in books, or they can be used in other ways than that. So our tag is a transponder. It emits a signal on its own, but only from the energy of receiving a signal that's telling it to emit that signal. So the tag gives us its encoded data by radio frequency when it passes a reader, and it's activated by the low level radio frequency magnetic field that transmitted by the reader. Now they're saying low level. At this point, this technology is being used quite a lot. A few years ago, well, more than a few years ago now, I attended the Defense Logistics Conference in Washington, and they were talking about using RFID tags on shipping containers containing all the supplies that the military needs, aircraft parts, POL, ammunition, whatever they need. And they were able to find them in essentially just a field that had a bunch of shipping containers by using their RFID readers. This is what an RFID label looks like. It has an antenna. That antenna, again, picks up the electromagnetic signature and is able to turn some of that into electricity that it then radiates out its own signal for the reader to read. Right, so it's very small, very thin. So RFID may eventually replace barcodes. Certain companies such as Malwart, Target, Metro AG in Germany, and the Department of Defense have mandated that having their suppliers use RFID on incoming materials. Right, so we have two kinds of RFID tags. The first is the passive tag. It has no power source of its own, but they make electric power from the magnetic field that the reader puts out so that they can signal back. They're very small. They're not very expensive, and they last quite a while. Active tags, on the other hand, have their own battery power packs, right? So they are self-powered. They have a larger memory and a longer communication range. So, but that does mean that they have a higher cost and they're used more specifically for high value items. So I have worked at a facility that had tags on all the major mobile equipment that they were using for production. And they had readers in every shop and every bay so that they could keep track of all their equipment very easily. All right, using RFID helps us with inventory management, supply chain management. We can use it for tracking systems, warehouse control, location identification, and to keep an eye on work in process. So it's really a very useful technology. So our RFID advantages, our identification doesn't necessarily depend on having physical contact or a direct line of sight to what we are keeping track of. We can keep more data in the identification tag than we can with most automatic identification and data capture technologies. And we can alter that data if we want to reuse the tag or if we want to update the usage of whatever it's attached to. Again, our big disadvantage is it's more expensive than most of our other automatic identification and data capture technologies. All right, so this compares our barcodes versus RFID. Our technology, barcodes are optical, and RFID is radio frequency. Read-write capability, barcodes are read-only, where RFID is read-write is a possibility. The storage capacity is more limited on barcodes, 14 to 16 digits, whereas on RFID it could be 96 to 256. We have to have line of sight for barcodes, but not for radio frequency identification. Barcodes, typically one-time use, whereas RFID chips are reusable. Our cost, barcodes is very low cost, and RFID is about 10 times as much cost for a passive tag. As far as durability, barcodes are more susceptible to having dirt, scratches, accidental marks on them, and RFIDs are more durable. So, okay, that's fine. Our other automatic identification and data capture technologies. Well, magnetic strips, of course, they've been used in credit cards and money access cards for years. They are more expensive than barcodes, and they have to be in contact with the scanner to obtain a reading. Optical character recognition. Well, the advantage there is it can be read by humans as well as machine readers. But you have a low first-time read rate. With machine vision, the typical application is inspection, but it can be used with 2D optical symbols. And there you go. All right, so that's the heavy excitement of automatic identification and data capture. Is there any question, or questions, I should say, about this? Okay, apparently not. That being the case, let's go ahead and move on to Chapter 13. And that is an overview of manufacturing systems. Now, a lot of this information you should have picked up one way or another in other classes. So, so be prepared to see what you've seen before. All right, so we're going to talk about components of a manufacturing system and types of manufacturing systems. So a manufacturing system is a collection of integrated equipment and human resources whose function is to perform one or more processing and or assembly operations on a starting raw material part or a set of parts. So our equipment includes production machines and tools, material handling and work positioning devices, and computer systems. So our human resources, depending on our setup, may be required full-time or periodically to keep our system running. Pardon me. All right, so we've seen this illustration before that talks about what do we need on the enterprise level, what do we need on the factory level, manufacturing support systems, manufacturing operations, quality control, etc. So again, our components of a manufacturing system are production machines, our material handling system, our computer system to coordinate and or control the preceding components, and our human workers to operate and manage the system. Okay. The part that may be missing, depending on our situation, is that computer system to coordinate and or control. But more and more, computers are being brought in to aid in our manufacturing processes, hence the name of this course, Computer Aided Manufacturing. All right, so production machines are modern manufacturing systems. The actual processing and or assembly work is done by machines or with the aid of tools. So the way we classify these production machines, we have manually operated machines that are controlled or supervised by a human worker. We have semi-automated machines that perform part of the work cycle with some form of program control, and the worker tends the machine for the rest of the cycle. Or we have fully automated machines that operate for long periods of time with no human attention. So in our manufacturing systems, processing and assembling parts and products, we have to have material handling functions like loading work units at each station, positioning work units at each station, unloading work units at each station, transporting work units between stations in multi-station systems, and temporary storage of work units. Okay, so we may have some of these, but not all of these in a manufacturing system. when we talk about transporting work in between stations, generally we have two categories. One is fixed routing. Our work units always follow the same sequence of workstations. So usually production lines are of this category. In fact, they say exemplify this category. And we can have variable routing, where our work units move through a variety of different station sequences, right? So this is more the idea of the job shop. All right, so here we have some illustrations for fixed routing. We have starting work units. They go to the first station, they go to the second station, and so on down the line until we have completed work units. When we talk about variable routing, we still have our starting work units, but they are going to different workstations depending on what they are and what they do. All right, so as I said earlier, it's very unusual not to have computers involved in putting together our manufacturing processes. So those functions that they have in a manufacturing system communicate instructions to workers, download the part programs to computer-controlled machines, control material handling system, schedule the production, diagnose our failures when we do have malfunctions, keep up with safety monitoring, quality control, and other operations management. Okay, so, and again, computers can be involved in any of these, but they're not necessarily involved in them. And our human resources, the third leg of our three-legged stool, so to speak, in a manually operated manufacturing system, it is those workers that are performing the value-added physical work on parts and products. In automated manufacturing systems, the direct labor may be doing things like loading and unloading the parts, changing and sharpening tools, but having an automated manufacturing system also means we have to have computer programmers and operators, we have to have numerical control part programmers, and we have to have maintenance and repair personnel. The day will come when all of this will be robots programming other robots, but it's not here yet. The types of manufacturing systems, well, we have four factors that are going to distinguish between different manufacturing systems. There's the types of operations, the number of workstations and system layout, the level of automation, or manning level, and the system flexibility. So, when we talk about types of operations, we have processing versus assembly operations, the types of materials processed, the size and weight of work units, and the part geometry. If we're talking about machine parts, then it is rotational versus non-rotational parts. For part or product complexity, if we're talking about assembling products, then it's the number of components in the product. For individual parts, it's the number of operations that we have to do to complete the process. All right, so the number of workstations in a facility is one of the measures of the size of the system that we're using. So if N equals the number of workstations, individual workstations can be identified by a subscript I, where I equals 1, 2, ... up to N. The number of workstations affects our performance factors such as our workload capacity, our production rate, and our reliability. So as our N increases, that means that we have greater workload capacity and a higher production rate. And we want, of course, for there to be a synergistic effect from multiple stations working together as opposed to N single stations. So our system layout, first of all, it applies mostly to multi-station systems. Whether we have fixed routing or variable routing also makes a difference. When we have fixed routing, we usually have our workstations arranged linearly or in a U shape, depending on our schema. In variable routing, we have a variety of routes available, and so that means that it's a variety of different layouts. The system layout is a big factor in determining how our material handling system works. All right, so our level of automation obviously makes a difference. The levels of workstation automation, we might have purely manually operated, we might have semi-automated, or we might have fully automated. Our manning level, M sub I, is the proportion of time the worker is at station I. So MI equals 1 means that we have to have a worker at that station all the time. MI is greater than or equal to 1 indicates that we have manual operations, and MI is less than 1 means that we have some amount of automation, whether it's only a semi-automation all the way up to full automation. Our manufacturing flexibility is our degree that our system can adapt to changes in operating requirements, which might be the production schedule, either a change in the part mix or the production quantities, or to equipment breakdowns. The other part of that might be variations in parts or products, such as our starting materials, our part geometry, our introduction of new parts or product designs. And these are optional this also depends on, do we have optional features in assembled products? All right, to enable our flexibility, first of all, we have to be able to identify what are the different work units. If we can't identify the differences between work units, we won't know what is the correct processing sequence. Quick changeover of operating instructions. So our work cycle programs have to be available to the control unit and quickly. And quick changeover of the physical setup. We've got to be able to change out our jigs, fixtures, tools required for the next work unit in a minimum amount of time. So, our classification of manufacturing systems, we might have single station cells where n equals 1. We might have multi-station systems with fixed routing, in which case n is greater than 1. And we might have multi-station systems with variable routing, in which case we're still saying n is greater than 1. All right, so our classification of manufacturing systems, as you can see here, we start with the idea of manufacturing systems as a whole. That splits into single station cells, multi-station with fixed routing, and multi-station with variable routing. Under single station cells, you either have manned machines or automated machines. Multi-station fixed routing, you have a manual production line or an automated production line. And with multi-station variable routing, we either have cellular manufacturing or we have flexible automated manufacturing systems. So, with our single station cells, of course, n is equal to 1, as we said. Again, we've got our two categories, manned workstations or fully automated machine. Right? So it could be n equals 1, m equals 1, or n equals 1 with m less than 1. This is the system that is usually used. It's the easiest and least expensive. It's more adaptable, more adjustable, and more flexible. And we can convert it to an automated station if the demand for the parts or products that we make there justifies it. Again, we never automate just because it's neat or cool. It's always for sound economic reasons. All right, so a multi-station system with fixed routing, and our most common way of doing that is a production line. A series of stations, workstations laid out so that the part or product moves through each station and a portion of the total work content is performed at each station. Our stations can be manually operated or automated, or a combination of those. We can use this idea for processing or assembly operations. And usually we're associating that with a mass production paradigm. Our multi-station systems with variable routing, again, n is greater than 1. So we have a group of workstations where we produce a limited range of part and product styles in medium quantities. So we have families of parts that we're producing that require similar but not identical processing operations. Assembly of a family of products requiring similar, but again, not identical assembly operations. And production of a complete set of components used to assemble one unit of a final product. This is typical in cellular manufacturing. All right, so there you go. Good. Are there any questions on chapter 13? I'm taking that as no questions, since either that or I've gone deaf in the interim. So where is my cursor tonight? All right, so we've covered chapters 12 and 13 in this class, and my voice is running out of gas here. So I don't think I'll start chapter 14 today. We will pick up with that on Monday. One last chance. Any questions? Hearing none and seeing the shaking of the head of the one student who's here in class, I'm going to call this class at an end and have a good weekend. Please be safe. Oh, what a day, what a day. Marcy, is everything okay?
Yeah. I got one more midterm to do.
I'm sorry, your mom is in the maternity ward?
No, I said I got one more midterm to go do.
Oh. Sorry to hear that. Oh. Man, I am just flat ass worn out.